Welcome back, everyone. Today I wanted to give you a sort of executive summary of what we've talked about with Diophantine equations. So we started with a really broad goal, which was to solve polynomial equations in many variables with solutions exclusively in the integers. So, for example, if you think about Fermat's last theorem, it says that if you look at the equation a to the 7th plus b to the 7th equals c to the 7th, that this only has solutions where at least one of a, b, and c is 0. So this is a polynomial equation of degree 7 in 3 variables. Now, one thing we noticed rather quickly was that when you have an equation like this, you can relate the question of integer solutions to this equation to a question about rational solutions to an equation in one fewer variable. And what's special about this is that the degree of every term here is 7. So there are 7 total variables in each of these. And so the way I do that is I just take this equation and I divide every term by c to the 7th. And then I go ahead and make a small change of variables where I go ahead and let a over c, I'll call that x, and b over c, I'll call that y. Note that x and y are now rational numbers because I took an integer and divided it by an integer. And so likely these things are no longer themselves integers. Probably they're just regular rational numbers. But with this change of variables, I now am looking to solve the equation x squared plus y squared equals 1. Now with x and y in the rational numbers instead of in the integers. So over time, we sort of backed into saying, really, we're going to narrow our focus to things that we can have some success with. And so the things we've had the most success with are 2-variable polynomials of degrees 2 and 3. So the vast majority of what we've done has been framed as finding the rational solutions to 2-variable polynomials, either of degree 2, or quadratic, as I usually say, or degree 3, which are the cubic things, which then sort of correspond to elliptic curves. So let me go over a particular example of solving something of degree 2, and then talk from there about how this works in general. So here's a particular quadratic in 2 variables. I want to find all of the solutions to x squared plus y squared equals 3xy minus 5 in the rational numbers. Note, if I wanted to, I could homogenize this and write this as a squared plus b squared equals 3ab minus 5c squared. And then I could be asking for solutions to this homogeneous quadratic in 3 variables. But that will just make things a tiny bit messier. I'm going to focus instead on just thinking about the rational solutions to this thing. So the first thing you have to do is find a solution. Now, note you're not guaranteed that there is a solution at all, but if you're going to find all the solutions, and there is at least one solution, well, you're going to have to find one to start this process that I'm going to describe. In this case, one solution you can find is xy equals 2, 3. 2 squared plus 3 squared is 13. 3 times 2 times 3 is 18, minus 5 is also 13. So this is a solution. And this is a point on our curve, so I'm going to go ahead and give this point the name P. So after I've done that, I'm going to go ahead and choose my favorite rational number as the slope. So I'm just going to call that number m, uncreatively, for slope. Well, m, in fact, stands for montre, which is the French word for to climb. But anyway, that's what we usually use for slope, because s's look like 5s, so s would be a bad choice. So we'll choose this, and then we'll write down the line of slope m through p. And that will be y equals m times x minus 2 plus 3, or mx minus 2m plus 3, whichever of those you prefer. Then we're going to find the intersection of our line with our curve. So how do we do that? Well, this is an equation of the form y equals some stuff, so I'm just going to plug this y equals some stuff into my equation that I started with. So I'm going to get this admittedly not very appealing mess. And I'm going to just FOIL this all out and move everything over to the left-hand side. So this is all going to go by very quickly for you, but this is going to take a little bit, and that's okay. There's going to be a fair bit of algebra involved in this section. And so we'll go ahead and push everything from the right-hand side over to the left. And then we'll group by terms. So in front of x squared, I have an m squared minus 3m plus 1. In front of x, I have a minus 4m squared. And then, let's see, I have here a 6mx plus an extra 6mx from the other side. So that will be 12mx. And then I have this 9x that's going to get swept over to here. So that is going to be a minus 9. Sorry, that x should not be there. Times x. And then plus all the constant stuff that has no x's in it, which is going to be a 4m squared minus 12m. And then I have a plus 9 plus 5, so plus 14 equals 0. Now, this is pretty bad in terms of mess, but I want to point out, again, this is a quadratic where we know one of the roots. And so if I make this into a monic quadratic by just dividing through by the term in front of x squared, I actually know that this coefficient here is negative the sum of the roots. And so I can use that fact then to find the other root of this polynomial without having to do anything horrible like plug this into the quadratic formula, which I very, very much do not want to do. So again, this is going to be negative 2 minus our other root, whatever you want to call that other root. So we can go ahead and figure out what does that mean our other root is. That means our other root is negative 2 minus this number. So our other root here is x equals negative 2 minus this, so plus 4m squared minus 12m plus 9 divided by m squared minus 3m plus 1. We'll go ahead and clean that up into one simple fraction. And my corresponding y here, I get by going back to the equation of the line, which is all the way back here. So y is going to be m times x, so that is m times that mess, minus 2m plus 3. So let's go ahead and work this all out. So we're going to put this all over our denominator. So this is going to be 2m cubed minus 6m squared plus 7m minus, and now when I put this over this denominator, that's going to be minus 2m cubed plus 6m minus 2m. And then when I put 3 over this denominator, that will be plus 3m squared minus 9m plus 3. Sorry, that got a little messy there at the end. Okay, so remembering what our x was before, let's take our moment of truth and see if this works. Let's plug in some relatively simple m. So I will plug in m equals 2 and see what that gives me. That will give me x equals 8 minus 12 is minus 4 plus 2 is 3 divided by 4 minus 6 plus 1 is minus 1. So one thing that turns out to be true about this is that if you do not do the algebra correctly, it will not work out correctly. So for those of you who are attentive, you may have noticed this should be an m squared, because this came from putting minus 2m over this denominator, so that should have been a plus 6m squared. Which means that when I work out what y is over here, then y, instead of being this, y works out to be plus 3m squared minus 4m plus 3 over our denominator. And so if I plug in m equals 2, now I get 12 minus 8 plus 3 is 7 over minus 1, which is minus 7. And if I check minus 3 minus 7 back into our original equation that we were looking at when we started this, see that minus 3 and minus 7 square to 9 and 49, so the sum here is 58, whereas 3 times 3 times 7, or 3 times minus 7, would be 63 minus 5 is 58. And so once you do the algebra correctly, you in fact get this solution. And so the big important fact here is that all rational solutions come from plugging a particular rational number m into this formula. So if you want to impress your friends by generating ridiculous solutions to this original random equation that we started with, you can just pick a weird rational number and plug it in here. So, for example, if you happen to choose m to be 3/17, then you would generate the new solution to this equation, q equals 347/29, 138/29. And this will make you many friends at parties. And so if you want to know what this looks like graphically, here's our curve, that is x squared plus y squared equals 3xy minus 5. That's shown in red. Circled here is the point 2, 3. And then the blue line is the line of slope 3/17 through the point 2, 3, which we can see intersects the curve at one other point, and that point happens to be over there. For comparison, here's the picture if instead of taking the line of slope 3/17, we went back to our very first example where we took the line of slope 2. That slope is steeper, so you can see here instead of intersecting the graph in the upper piece, it now actually intersects the graph at the bottom, which is why we ended up getting a point where both x and y were negative. Namely, the second point there is -3, -7, as we calculated before. So the moral of all of this is that often we can find new rational points from old rational points by connecting the right lines through those points and finding the intersection with the curve. In the case of quadratics, you just find one point, take any line of rational slope you want, and that will give you a new point, be it -3, -7, or 347/29, 138/29. But this will give you all or all but one solution. The times where you miss a solution are when there's another point on the vertical line, in which case you have to be a little bit careful. But you get all or all but one of the solutions. And so one consequence of this is that every quadratic either has infinitely many solutions, and those solutions end up being dense in the curve, or it has no rational solutions at all. In other words, maybe you got stuck all the way back at step 1, and you couldn't even find a solution to get started. But as soon as you find a single rational solution on a quadratic, you get this dense collection. Next, I want to talk about what happens with cubic curves. Now, for our sample cubic curve, I'm going to take y equals x cubed minus 10x plus 4. And I'm going to talk about a couple different ways that we can use this idea of intersecting the curve with lines in order to find more points on this curve. But, just as before, we can't do any of these things until we can actually produce a point on the curve. So to start with, I want to write down all the points we can just sort of see by looking on this. And so there's a few that I rigged to be on here. So one is that if x is 0, this right-hand side is 4, and so that would match 0, 2, and 0, minus 2. Another you can see is that if x is 3, you get 3 cubed, which is 27 minus 30, which is minus 3 plus 4, which is plus 1. And so that will, in fact, give you 3, comma 1 is a point on this, because 1 squared is 1. So is 3, comma minus 1. Note, the structure of our equation guarantees that our points come in pairs, because if a particular y works, I can always just flip the y over. This won't work for all cubic curves, but it will work for all cubic curves that look like y squared equals, and then some function of x like this. Now, if you dig just a little bit harder, you might notice that if you take x to be minus 2, that actually makes the right-hand side here minus 8 plus 20 is 12, plus 4 is 16, and so that will give you the point minus 2, 4, minus 2, minus 4. So just by looking at this curve, you can find a handful of points, but you're going to pretty rapidly run out of points that you can find just by guessing coordinates. But on a cubic curve, one thing we can do is any 2 points we already have, we can draw a line through, and that line should intersect the curve in a third point. Again, basically a curve of degree m and a curve of degree n should intersect in m times n points. So, in particular, a line which is of degree 1 and a cubic should intersect in 1 times 3, which is 3 points. And so if I draw the line through 2 points on the curve, that should give me 2 of the intersections. The third intersection should be there, and it should also be rational if the first 2 points are. So having generated these 6 points to start with, I should be able to just pick 2 of them, draw the line through them, find the intersection, and that should give me a new point. Note, by the way, this will not work if I pair the 2 points which have the same y-coordinate except negated, because this will give you a vertical line, which if I pull up the graph here, you will see will in fact not intersect the curve at a third point. You can see borne out in the picture the mirror symmetry I talked about, where you're allowed to flip the y. That's shown by the fact that this graph is symmetric across the x-axis. But you can also see that any vertical line, in fact, only hits the graph twice. We'll later claim, and you can believe this or not, that the vertical lines through this graph also intersect this graph at some point at infinity, whatever exactly we decide that means. But we're going to put that aside for now and just say, when you try and do this process, don't pick 2 points that are on a vertical line. It will not be helpful. So, without too much thought, I'm going to pick this point and this point. And let's try working out what new point we get out of taking the line through these 2 points. So the first thing I have to do is figure out what is the equation of the line through these 2 points, which I should be very well equipped to do. So the slope of this line is minus 4 minus 2, which is minus 6, divided by minus 2 minus 0, which is minus 2. So the slope of this line works out to be 3. And so my equation of my line through these 2 points is y equals 3x plus 2. And now, just like what I did before, in order to find the point of intersection, I'm going to plug this 3x plus 2 in for y. And I actually don't even really need any fancy tricks here. I can just factor this. And when I do, I should hopefully find that I get 2 of the roots being the x-coordinate of each of the points that I picked. Because definitely, the curve that I started with, and this line through these 2 points on that curve, had better intersect at least these 2 points. And so I definitely get an x equals 0 and an x equals minus 2 here. But then I also get a new x, which is x equals 11. And that should correspond to a y that should be given by my y equals 3x plus 2. So that is to say y should be equal to 35. So what we seem to be claiming here is that 35 squared is surprisingly the same number as 11 cubed minus 10 times 11 plus 4. And that's a neat fact, that if the last fact did not impress your friends at parties, this definitely will. Now, the nice thing is, I can repeat this process. So, I have the point here, minus 2 minus 4, and the new point, 1135. And with these points, I can do exactly the same thing. So I can find the slope of the line between them. 35 minus 4 is 39, divided by 11 minus 2 is 13, which gives me 3. And so my equation of my line here is y equals 3x plus 2. Now, why didn't that work? Well, if you think about it, what did we just do? Well, we said, okay, there's some third point on the line between 0, 2, and minus 2, minus 4. That third point is 1135. Okay, so there's some third point now, we're saying, on the line between minus 2, minus 4 and 1135. Well, gee, I wonder what it is. Oh, right. It's 0, 2. So when I said you can do this again, you have to do it again with a slight twist. And the slight twist is I have to modify one of these points just a bit. But remember, I can always just flip a sign on one of these points. Because, again, my particular curve has this form y squared equals blah, 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 so I can just change the y. So let's do the same thing, but instead of doing it with minus 2, minus 4, and 1135, which was going to, at the end of the day, tell us that, hey, 0, 2 was on the curve, which would have been disappointing. We'll instead pick minus 2 plus 4 and 1135. So my slope here is now going to be 31/13. Already, that's a little bit less nice than what we were dealing with before. And so the equation of my tangent line here is y equals 31/13 times x plus 2 plus 4. So, plug that in to y squared equals x cubed minus 10x plus 4. And now at this point, I am working with the number 31/13, and I'm about to square it. I definitely at this point want to use all of the algebra trickery I can, because this is not going to factor as nicely as this previous version at all. And so by way of doing that, I'm just not even going to think about what the b of this y equals mx plus b is. And I'm going to show you that actually just from the slope, we can find the other point of intersection. And here's why. When I square this out, I'm going to get 31 squared, which happens to be 961, over 13 squared, which is 169, x squared, plus, and then I'm going to get some complicated number times x, plus some complicated constant equals x cubed minus 10x plus 4. And I'm going to move all of this over here. And so I will get x cubed minus 961 over 169x squared plus, and then again, some x term, some constant term equals 0. Note there was no x squared term over here before, so this is the entire x squared term. And here is where we use our trick that this number, the negative of this number, I should say, is the sum of the roots of this polynomial. And that's because, again, this is a monic cubic. That is, it's a cubic where the leading coefficient is 1. So the sum of the roots is 961 over 169. On the other hand, we know two of the roots are minus 2 and 11. Again, we rigged that to be the case. So the sum of the roots is minus 2 plus 11 plus, and then our new root. And so what that means is that our new root is 961 over 169 minus 9, which, as it would happen, is minus 560 over 169. So our new point then has x-coordinate minus 560 over 169. And to get the y-coordinate, quotes unquote, all I have to do is plug this x-coordinate into this formula for y. And upon doing that, we are happy to discover that the y-coordinate of our new point is negative 1906 over 2197. And so through this process, on this particular cubic curve, we can generate an infinite number of points. Just keep drawing lines through pairs of points we know, find the intersection, and you will find points of increasing complexity. And by complexity, I just mean the size of the numbers involved, because the numbers involved will get much more complicated much more quickly. But they're still rational, and that's what we care about. We care about where the rational points on this curve are. But even though there are infinitely many rational solutions to this particular cubic, there are, in a sense, far fewer of them than there were to the quadratic that we talked about earlier. And by that, what I mean is that they're very spread out and complicated. So that's one method to generate new points on a cubic. But this method was based on the fact that we needed to generate a bunch of points to start with, at least two that had different y-coordinates or y-coordinates that weren't plus and minus of each other. So you might ask, what can you do if you only have 1 point? And if you have only 1 point, you can cheat and do this a different way. So instead of using what's called a secant line, that is a line that goes through the curve at 2 points, we can use a tangent line, which is the same thing you talked about in calculus, where you take a line that goes in the same direction as the curve. And as we've seen so far, for some reason, geometry seems to identify intersections at tangent lines as being fundamentally different from other sorts of intersections. And in particular, intersections at tangent lines seem to count double. And so effectively, when we take a tangent line to the curve, what we're really doing is we're drawing the line through this point and itself. And somehow, because of the curve, that gives us a well-defined tangent direction. It gives us a well-defined line. That line intersects the curve twice at that point and then once at a third point. And that third point we can find. So what I want to do is I want to do that once for you with one of these points. So I'm going to start with my point 0, 2. And I'm going to talk about how we're going to find the tangent line at this point. So here's our equation. And to find the tangent line at this point 0,2, what I'm going to have to do is use implicit differentiation. So I'm going to take the derivative of both sides here, and every time I take the derivative of something with a y in it, I'm going to inherit a y prime. This y prime is secretly coming from the chain rule. If you want to figure out where this is going, we're thinking, okay, y is somehow depending on x. So when I take the derivative of y squared, I take the derivative of the outside, evaluate it at the inside, multiply by the derivative of the inside. This is exactly the chain rule. And so using this somewhat weird differentiation method, we get the equation for the slope of the tangent line at any particular point we want. Of course, we want the slope of the tangent line at this point. So that is the point where x is 0 and y is 2, which will work out to be minus 10 over 4, or minus 5 halves. Thus, the equation of our tangent line is y equals minus 5 halves times x plus 2. And just like before, we're going to plug that in to our equation. Just like before, I can take advantage of the fact that I know 2 of the roots of this polynomial. 2 of the roots of this polynomial are 0. And so if I want, I can only pay attention to the x squared term. But just to show you that it still works out, because the algebra here is not going to be so bad, I'm actually going to work this out entirely. But just like before, if you wanted to, you could completely ignore everything but this term squared, and then use our rule about the sum of the roots, showing up as the negative of the x squared coefficient. Okay, so when I multiply this out, I am going to get 25 fourths times x squared minus 10x plus 4 equals x cubed minus 10x plus 4. And so then I'm going to move everything over. I'll get x cubed minus 25 over 4 times x squared. Actually, that's it. Now, note that what I said about the intersection at the point of tangency being a double root is borne out here. Namely, the point of tangency here happens at a point where the x-coordinate is 0. So I can go ahead and factor out an x squared, and we'll see that, yes, that showed up twice. And so this fact that intersections at the point of tangency count double is really borne out in the algebra. It is not a completely made-up thing, as much as it seems like, well, that's awfully convenient. But it really does work out that way. So that is our point of tangency, where we have the double root. And then here is our third point, where x is 25 over 4. Once x is 25 over 4, then we know what y is, which is going to be 125 over 8 plus 2. And so that'll work out to be a 16 I need to add in the numerator. And so that will be minus 109 over 8. And so if you look at these two coordinates, that gives us a new point, yet another one, on this curve. And so to repeat, those are the two ways that we have to make new points on a cubic curve out of old points. If we have 2 points that are different, we draw the secant line through them and find the third point of intersection. If we have 1 point, we can draw the tangent line at that point, and that will intersect at some third point. And that will let us generate a bunch of points on a cubic curve, provided that we can sort of get started, and provided that there are a bunch of points to find. Because unlike quadratics, quite often it will happen that a cubic curve will have only a finite number of rational points. And that finite number might be as small as 0, or it might be as large as somewhere in the 20s, but usually it will be very small. Other curves, like this one, will have infinitely many points. that's all we have to say about cubic curves for now. In the next lecture and the next video, I'm going to talk about how to change a cubic curve into an elliptic curve. That is, what additional things am I going to think about and require in order to start genuinely calling something an elliptic curve? And these elliptic curves are going to then serve as the basis of a lot of modern cryptography. But that's all for now. I'll see you next time.